Hello everyone, I hope that you're doing well. In this video, I'm gonna explain the design and the simulation of the dipole antennas at 5 gigahertz. As you know, the dipole antennas is generated with the two arms, and there is a feeding in between of the two arms. So the length of the antenna is normally half a lambda, which is the lambda is the wavelength of the frequency, operating frequency. So it should be 30 millimeter at 5 gigahertz. And for the radius of this arm, I'm gonna put as 0.5 millimeter, and for the gap between them, I'm gonna put 0.5 millimeter again. So I'm putting this gap because I want to excite the antenna from this side. So as you see, this is the ideal form of the length for the dipole antenna, and it is 30 millimeter. But practically, there is an ending effect, and we have to put it a little bit smaller than the ideal 30 millimeter to be resonated at the exactly 5 gigahertz. So I will show you at the end that 26.5 millimeter is the practical form of that, which is resonating at 5 gigahertz exactly. But with this length, it will we will have a bit of the resonance frequency shift. So to start this design, I'm gonna explain how to do that. So first of all, we have to draw the structure. We go over the draw panel, and we have the cylinder here. I'm gonna add the cylinder. So as I explained before, we are gonna define the antenna as a parametric. So here I can choose the center position of the antenna. So I'm gonna put it as 0 millimeters. Okay. So we can put it again 0 millimeter, and I'm gonna start from a bit top, which is including the gap, and it should be L gap over 2. It will start from here. So for the gap that we explained, I'm gonna put it 0.5 millimeter. Click on OK. For the radius, I'm gonna put it like a R uh, antenna, so it should be 0.5 millimeter again. So as we have the millimeter at the unit type, we don't need to add it. And for the height of the antenna, I'm gonna put it the L antenna, which is going to over 2. This is the L of the antenna, so I'm gonna put it as a 30 millimeter, which should show us a 50 millimeter because we are using half of that. So now I'm gonna go to the attribute, so I can define it as like a dipole arm 1, and the material should be PEC or copper. I'm gonna put the copper here. Okay. So it should be system defined material. So we have to use this one. Click on OK. So we don't want it to solve inside of that. I'm gonna uncheck it. And for the color, I'm gonna put this color similar to the copper. So everything is fine. I'm gonna click on OK, and it will show me the arm that I have generated. So the next step of that is just we can mirror this one, or we can rotate it on the X or Y direction. So I'm gonna click on this one, arm 1, and I can rotate it I can mirror it with this one, so in the Z direction. So as you can see here, it is mirroring. So this is a preview of the design. I'm gonna click on OK. So now we have the arm 2. I can change the name to arm 2, and it's a copper, and everything is fine. So we have it here, as you can see. So the next step is just going to and defining the excitation. For the excitation, we can define like the coaxial cable simply, or we can go with the ideal excitation. I'm gonna go with the ideal excitation to because we need this ideal excitation in all the simulations. For the coaxial for the coaxial excitation, we have to draw the geometry of the coaxial here. So it's super easy. So I'm gonna go with the general one, which is the excitation uh, with the sheet and the port. So for that reason, I'm gonna go and add a sheet here because for the lamp element excitation, I need a sheet. And for this sheet, I have to define the position. So it is from minus R antenna, and it will be 0 here, and it will be minus L gap. So now it should be in the y direction, and the width should be 2 cross R antenna, and the length should be L gap. So as you can see here, it should normally cover both of them. So maybe I have to change this to 1 and change this to okay. Okay, it should start from minus L gap over 2, and it will go to the 2 cross L gap. So as you can see here, I'm gonna name it as a port 1, and so the color can be the same color. That's it. So we have now the sheet here. So I'm gonna excite it. So what I'm doing, I'm selecting the face mode. So right click and selection mode. I'm gonna go over the face and select this one, and right click on that. Add the assign the excitation port. Again, you can see that we don't have the lamp port or the wave port. So what I have to do, I have to change the go to the HFSS solution type and make it a modal simulation. So again, I'm gonna select this face and add the port. So assign excitation port. I can put the wave port or lamp port. I'm gonna go with the lamp port. So it is in the 50. The full port impedance is 50, and I'm gonna define the integration line. So it will start from here. So you have to see the triangle, and it will go to the here. So click on finish, next, and finish. So now here we have defined the geometry. So we have defined the excitation, and that we have to go over the boundary. For the boundary, simply we can go over the create a region and click on that. So you can change it to the absolute offset, and you can make it like maybe 20 millimeter, and click on OK. So it will show you the box, and we have to define this box boundary. So I'm gonna click on the region, and for the assigning the boundary, I can go over the radiation. So click on OK, and now we have the boundary, we have the excitation. We need to simply define the solution. So we can go to the HFSS, we can go then over the analysis setup, add solution type, and then go over the advanced or auto. I'm gonna go with the advanced. So we're gonna do it on the broadband. It was supposed to be operated in the 5 gigahertz. I'm gonna start from 4 till to 6 gigahertz, and I'm gonna put as a maximum number of the passes as 10. I don't want to change the maximum delta S in this case, but for the minimum number of the passes, I'm gonna put it 2, and the minimum coverage passes, I'm gonna again put it number 2. So here it is going from the 4 gigahertz till 6 gigahertz, a number of point. I'm gonna make it 201 and save all fields. So I have designed this one, and now we can check that what we have missed. We are validating that one, so everything is fine. We simply go over here and click on that to simulate the uh, design antenna. So it's gonna simulate it. Now we can go over the radiation and insert the far field setup because we wanted to see the results on the far field. So we're gonna add the infinite sphere. And for phi, it is from a minus 180 degrees to 180 degrees with the steps of the 2 degrees. For the theta, I'm gonna go over from the again 100 minus 80 degrees till 180 degrees over the with the steps of the 2 degrees. Also, you can name it like here, or you can choose the coordinate system for that. So I don't want to change it. If you have a different coordinate system, you can change it. I'm gonna click on OK, and as you can see, my simulation has done, and I can go over the result. So first of all, I wanted to check the reflection coefficient. So I can simply right click on the result and go over the create model solution report and choose the rectangular plot. Here I can I can check all the parameters as you can see here. So we have to first select the solution, and here our solution is the adaptive passes with the sweep. So I'm gonna check for the sweep of the frequency. Here you can check the domain. So I'm gonna go with the frequency domain. And now this is the S11. And for the S11, I can check all the values in dB, in imaginary or the real part. I'm gonna check the dB part because it's important for me. So here you have the families. If you have any variable that you are changing to check the result, you can select that variable here. And now we can create a new report for that. And this is the S11 of my antenna. As you can see, there is a shift in the resonance frequency. It was supposed to be 5 gigahertz, but it has a shift here. So practically it should be on the 5 gigahertz, but with the lower antenna size. This is 30 millimeter as I explained to you. I have another design here. I just wanted to show you so this antenna length is 25.5 millimeter, and if we check the results here, it is around 5 gigahertz. So with the length of the antenna, we can shift the resonance frequency definitely. So now I'm gonna go over to our design, and we have the S11, and the S11 is showing that how much of the power has been penetrated to the antenna and it's radiated by the antenna. Other than that, we can check the other results for like the Y parameters, Z parameters, VSWR, and I just wanted to show the VSWR and the absolute value. This is the Okay, this is the VSWR. It is between 1 and 2. So VSWR is normally should be here to have a better radiation. And then now I can go over the far field and plot the far field results. So we can plot the like the 3D polar plot. And here you can check the directivity, realized gain, or the gain. So the difference between the directivity and the and the gain is like the aperture efficiency, and the difference between the gain and the realized gain is that if you have like multiple matching networks on the design, and if you wanted to check all the effects from the port till the radiation, you have to use the realized gain. But normally we are using the directivity to check the directivity of just the antenna that we is under our test. Okay, so I'm gonna go over the directivity, and I can select the total directivity, or even you can check the copolar directivity, cross-polar directivity here. So I'm gonna go with the co and cross, and for them I'm gonna have the dB4, as you can see here. So here I'm gonna get it in the 5 gigahertz. Also, I wanted to show it in the 4 point maybe 50, yeah, 4.50 gigahertz. So I can select that. Here it is not showing, but if we change it to the solution to the SWIP, so then we have the option here to check for like a 4.5. I'm gonna check it on the 4.5 and create a new report. So as you can see here, this is the radiation pattern of the antenna, and the maximum radiation directivity is 2.47. And if you want, simply you can show it on your structure to see that how your structure is radiating. Simply go here and right click on that and show in the modular window. So if you double click on this one, you will see that on your structure. So your structure is radiating uh, in the side directions. So in the x, y, and y directions, as you can see here. Also, we can go here and right click on that far field. We can have a polar plot, not a 3D, but we can have a polar plot with the radiation pattern. And here is the gain, total gain. We can go over the dB, so we can select the phi. I'm gonna select phi in the 0. There is no difference between them because it's symmetric. And so it is the phi 0. I can change it like 4.5, and as you can see here, and generate a report. So this is showing us the radiation pattern. If we change the phi, there's no difference because it's completely a symmetric structure. And also you can go here and go to the far field and plot the rectangulars. And this rectangulars, again, you can plot the gain or the directivity, any of them, and you can select the dB. So I just wanted to show you the copolar and cross-polar in a dB form, and I'm gonna put it on the 4.5, and for the like only one of the phi, which is in 0. So we have all of them. Generate the report, and as you can see here, this is the copolar form and this is the cross-polar form of the antenna, and there's a good difference between the co and cross pole on the broad side. So the antenna is working very well, and the maximum gain of the antenna, you can right click on here and add a marker. So this marker will be here, and it is showing us 2.53 dB for the gain. So this is the overall of the results that we can see. If you need the results to plot in the MATLAB for the reports that you need, you just simply need to right click here and export the results. And here you can use the separate columns for the curves if you have many different results, as here we have the copolar and the cross-polar. So you can like name your file gain plot to, and you can choose that which file you wanted to get. Normally I'm getting the CSV, so you just need to select the direction here and save that file. That's it. This is the overall of the design uh, of the dipole antenna. Thank you for watching and have a wonderful day. Bye bye.